is the beginning of philosophy of thinking machines. And artificial intelligence is about emulating those thinking mechanisms. And probably you have heard of Turing test. So the Turing test is there is a person sitting on the other side of the room. Can you hear me? So the person is sitting on the other side of the room, and the machine is on the other side, and in between there is an interrogator. And the task of interrogator is to know which response is coming from the machine and which response is coming from the human. If interrogator doesn't recognize which is machine and which is human, then machine is called to be intelligent machine. So how many of you think that ChatGPT has passed this test, or large language models have passed this Turing test? How many of you? Only a couple of hands. Hello. So actually in my class there is no gray level, so it's binary. So either you say yes or no. How many says yes? And how many says no? Still is gray level. I am coming from image processing background. I don't like gray levels. I need black and white. Threshold yourself. Again, how many of you think that large language models are intelligent according to Turing test? Okay, no more hands. Okay. But the catch in this paper, interrogator has to be expert, subject expert. So if let's say my mother says ChatGPT or this large language models, they are very intelligent. They can answer anything. But if I put something regarding to machine learning and ask large language models, sometimes they give rubbish answers. So within couple of minutes, you understand that this is a machine. For me, still that large language models are not that intelligent to beat subject expert. So all of this domain started with the premise of creating something that we see over here. This is what is going around in our brain. This is neurons firing in response to some activity, some stimulus. And this firing makes neurons work together, which we call neural network. It is said if they fire together, wire together, they will be wired together. So this is the premise to create something like this using some mathematical models. If you know how many neurons do we have in our brain? Anyone? How many neurons do we carry? Anyone? Million, billion, trillion, quadrillion? How many? 100? 100 billion. And how many synaptic connections? Said trillion, but okay, there's one more thing. If you read some neuroscience literature, be careful, because neuroscientists say that we can answer your question with 10% probability. Okay? So this is a heads up, and I'm not exaggerating it. So the rough estimate is we have more than 10 trillion synaptic connections in our brain, and that is why we say that we are more intelligent zebrafish. Have you heard of what is zebrafish? Okay. The question is, are we more intelligent than zebrafish or not? We cannot say, because zebrafish has only 1 billion synaptic connections. We have more knowledge. We can store more knowledge, that is for sure. That is why we have bigger heads. That is the only thing we know with certainty. But are we more intelligent? Question mark. I am not sure. Okay, so the first breakthrough in the history of artificial intelligence. Have you heard of these two guys? Anyone of you heard of these two guys? McClaw and Pitts. These are two neuroscientists, nothing to do with computer science. So when you have abstraction of the physical world using science, something big happens. And I will show you a couple of those breakthroughs when we consider how AI has evolved. So these two neuroscientists come up with the idea that, okay, we study neuron, we understand there is an axon, and if we combine electrical currents or in the vicinity of the neuron, if they are more than some threshold, they will fire. That is the only thing we know about neuron. So they come up with the abstraction of this using this kind of structure. Have you seen this kind of structure recently? So you have neuron. These weights are, by the way, synaptic connections. With the help of these weights, different neurons work together. Do we have AI students over here? Okay, so we have AI students. I got the answer from the, okay. Have you seen this kind of image before? This is 1943. And up till today, we are abstracting neuron approximately like this. So there is something like weights, there's an input, then we sum them together, and if they are more than some threshold, what is the threshold? In easy term, what is the threshold? Why we need to have a threshold? If I don't have a threshold, what will happen? Okay, she says something about limit. In 1943 article, they call this threshold as limiter. Thank you. This is called as a limiter. And why it is called limiter? Because we cannot deal with all the data. We need some zeros. If something is not big enough, I will suppress it. So right now, okay, one more question. Actually, I asked a lot of questions when I'm teaching. How many rods and cones or sensors do we have in our eye? Anyone? If you are looking at the image at the moment, how many sensors are getting simulated? Maybe in trillions. But how many neural connections are there from this eye or iris to the brain? Maybe some millions. So huge compression goes inside our brain. We cannot deal with all the data. And this is the premise of AI as well, because we are going to simulate what we have in our brain. So we need some kind of limiter, like divine power has given us this kind of limiter in our brains. We compress the data, right? Before I move forward, this is what we have. This is the latest neuron, or what we are dealing with these days. So again, we have some inputs, we have some unknown, which is written as theta. It could be anything. Any Greek letter would work over here. Then we sum them together, and then there's a function, which is a limiter. Now we call it as an activation function. That's all. That is the only difference we have made from 1943 till 2025. Exactly same thing. At that time, they were thinking about threshold. Now we have nonlinear threshold, some activation function. Okay, let's deep dive how actually neural network works. So if you have data from two different classes, maybe they are malignant or benign cells. I work with medical imaging, so we have that kind of a data. And what neuron will give us? A line. That's it. A linear surface. Maybe it's, if you know equation of line, it is mx plus c or ax plus b, whatever you want to call it. It's w1, x1, w2, x2, but it's the linear surface at the end. Okay, it's not a line, it's a plane. Okay, it's not a plane, it's a hyperplane. Because we don't have nouns for all the dimensions. We call it hyperplane. But at the end of the day, we have a linear surface that separates the data into classes. But again, then you say that there's some misclassification, right? In some green circles, I have red cross. How to deal with that? What we can do? So what line does, if you know mathematics, all the samples that lie on one side of the plane, they will give me some positive output for that equation, and all the samples on the other side will give me some negative value. And that is the classification. I just need to classify the data. So I have infinite number of decision boundaries, right? This could be decision boundary, another one, another one. But the real intelligence comes when you find the decision boundary, but not a decision boundary. The means the perfect to the level we can get. Right? So all the intelligence comes how you find these weights. Because I have this control, this is synaptic connection in our brain. This is how our brain works. When a lot of neurons fire together, we wire them together. I will talk about it. It is called synaptic plasticity. So all the intelligence comes down to the fact how to learn those weights to have that linear surface that classifies the data. So one of the earliest learning rule in neural networks was proposed by Donald Hebb. It is called Hebbian rule. Have you heard of that Hebbian rule before? Again, a neuroscientist. The core idea is often summarized as neurons that fire together, wire together. Fire together, wire together means if they are working together, if they respond to a stimuli in the same manner, we should make a network out of it. This is how brain is getting trained. This is how kid learns to talk. This is how kid learns to balance themselves. So there is a neural network. And I was asking how many neurons do we have in our brain? When we were like 2 years, 3 years, we have maybe 2 times more neurons in our brain. But as we get old, these neurons die because we were not using them. So this is the natural process of decaying of neuron as well. As an adult, we actually have half of the neuron as compared to once we were born. That is why it is easier for kids to learn a new skill because they have more neurons at that time. So if they start learning some new skill, they will train the network and they will retain the neurons for the rest of their life. Okay, coming back to Hebbian rule. If 2 neurons, say A and B, are active at the same time in response to some activity, okay, this is okay. I will use very few mathematical notations because I want to go through all the core ideas. But this equation is the core. This is Hebbian learning rule 1949. It says that some eta, now we call it learning rate, xi and xj. Xi is presynaptic connection, xj is postsynaptic connection. Pre means a neuron that is before the neuron that is trying to learn a weight, and post is afterwards. So if the neurons are working together, weight will go high. And eta, if eta is 0, it means we are learning nothing. If eta is 1, it means we completely trust our sensations. But this is not true as well. So eta is usually 0.2, 0.3. From the very beginning of AI, scientists came to the conclusion that this learning rate would be around 0.2, 0.3 because we cannot trust our sensations completely. And if eta goes to 0, we'll learn nothing. So this is the collective wisdom of all the scientists from the very beginning. Then comes delta rule. Anyone heard of this delta rule? Anyone have seen this equation like this before? Very familiar equation if you are into AI or deep learning or computer vision. It says that, everyone understand what is weight? Why I am trying to convince you that weight is important? Because this is how neural network is getting trained. If I move weight, it means the network, the neurons are closely connected. They are working together. If weight is light, it means synaptic connection is loose, right? So we are trying to learn this weight. And D is desired output, and Y is what neuron is giving me. Okay, have you seen this equation before? Have you heard of gradient descent before? Any one of you heard of gradient descent? Does this equation look like gradient descent? Nashta nahi kiya. Have you had breakfast? You had breakfast, okay. Is this look like a gradient descent? This looks like, to me it looks like a gradient descent, but it's a delta rule. Now we are not calling it gradient descent. We'll talk about gradient descent. Okay, moving forward. Then came the biggest breakthrough in 1950. This is 1958. This is perceptron. Then came this guy, Frank Rosenblatt, working for US Navy. So he was working for, this is Cold War era. Consider the fact we are in Cold War era. So there were a lot of money was pumped into defense projects by US Army. Before I talk about it, just read what I have highlighted. It says that neuron, expect, will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This is the height of exaggeration I can read in any literature. Even after 70 years, we are not able to achieve all the tasks. But just this guy proposed perceptron, which is a linear classifier, I will explain. It just draws a line between data samples, but this is what the news clipping says. This is exactly the same what you see in media today. जब वो flash होता है ना, breaking news. So this was a breaking news in 1959, and press clipping says that they have found the way a machine will reproduce itself, it will be conscious of its existence, it can walk, talk, and see. This is height of exaggeration. But what exactly was perceptron was this. Again, this perceptron looks like what we have seen before, 1943. Exactly same. But the good thing now, we have the learning algorithm. Before that, it was the abstraction that how neuron will work. But why perceptron is famous? Why Frank Rosenblatt is famous? Because he gave that learning rule, like how this neuron will be trained. This was the new thing. There is nothing new. Perceptron learning rules look like exactly delta rule. So these are jigsaw puzzles. Some guy found something, and after a couple of years, another scientist found that, okay, this is an interesting idea, I can use it. Right? This is how science progresses. So this is 1958, 59, perceptron. And still we are using same perceptron. You work in neural networks, this deep learning. This is the basic building block. The only difference is that function जो f वहाँ पे लिखा. At that time, we were talking about threshold. Now we have multiple activations functions because we know that we are working with deep learning. There's a problem of vanishing gradient, exploding gradient. We cannot have threshold. So there are better ways to do it. But the abstraction remains exactly same. Then this came, this gradient descent. But gradient descent actually was much older. Have you heard of the name Cauchy? Famous mathematician. Cauchy-Schwarz inequality, if you have done linear algebra course. I'm not sure, but have you heard of this? Okay, perfect. So this method of gradient descent is much older, proposed in 1947 for mathematical optimization. At that time, there was no concept of perceptron, learning rule, or anything. It was mathematical optimization. If you want to find maxima or minima of function, you take negative of the gradient. That we know from 1847. But this Arthur Samuel, this guy, he built a system that used gradient-like learning algorithm. So the idea came, okay, that learning can be done using mathematical optimization. Maybe it's much better. So this was the idea of gradient descent. So if you are walking on this surface, this is a search space in which your solution lies. Or in simpler terms, this is surface of cost function. And if you want to minimize the cost, you walk against the gradient to reach global minima or global maxima. It's up to you, it's your definition. Right? So this gradient descent was proposed in 1847. In 1960s, scientists rediscovered it, okay, that we can use the same idea to go down the hill to find the function minima, because this is like going down the hill, right? Then, actually, this is we called AI winter. I'm not going to go in the detail because of time constraint, but this actually, when perceptron was proposed, it was the hype that it can walk, talk, see, a lot of other things. But then the book was published, named Perceptron, which proved that perceptron is only a linear classifier, and it even cannot learn XOR data or exclusive OR data, because that is nonlinear. Only 4 data points. So that was the beginning of AI winter. But at the same time, we have something called multi-layer perceptron. Exactly what we have as a deep learning architecture these days. But funding was dried down. It's AI winter time. No one was talking about AI. But scientists have a very different view. They say, okay, we'll not do AI, we'll do machine learning. We can talk offline, but there's a difference between AI and ML. But scientists say, okay, we'll stop doing AI. Now we'll work on ML. Okay. I'll just catch my air, not like this, but like this. But this is multi-layer perceptron. Okay, same perceptrons, but if you want to have a non-linear surface, okay, I can have multiple perceptrons working together, like how it is done in our brain. Then we could have a non-linear surface. Simple idea. Okay, without this guy, we cannot have deep learning like we have today. This guy is Paul Verbos, 1974, MIT, not Stanford, I guess, Stanford PhD. He proposed backpropagation. Okay, we found gradient descent, but how to use it to train multi-layer perceptron? No one knew. No one knew. It was okay for a single neuron, but if you have 10,000 neurons, what we can do? So this guy came with his PhD thesis, and he said, okay, I don't know how to do it exactly, but I know that you have to put the error back into the network. That was his whole idea of PhD, that to train a deep learning network, calculate the error at the end, because this is a feed-forward network, multi-layer perceptron. Once you have the error, put it back in the network and learn something. He didn't give example. And that is why people forgot about his invention. He proposed that in 1974, and then he was rediscovered in 86 by Jeff Hinton, the same guy who got Nobel Prize of Physics, but he's a computer scientist, in 2024. Right? So backpropagation critics argued and still do that backprop doesn't resemble how real brain works. Okay. We are moving away from neuroscience-centered AI to mathematical optimization. Now mathematics is overtaking the whole field of AI. And Paul Verbos didn't have practical neural network training, which was done in 86 later on. So the AI community didn't immediately recognize the value. This is, again, something that science has seen many times. If you read history of science, something is discovered, but no one gives importance to that invention. And maybe after 50 years, 70 years, 100 years, someone rediscovered it and said, okay, we can use the same idea somewhere in the other side of the globe. They have different ideas. So this is one of those cases. Backpropagation is backbone of deep learning. Without it, there wouldn't be no deep neural network powering today's AI. Consider the fact. Without this, we will not have any AI that you are using these days. Coming to 1980s. Okay, we have some neural network, but the problem was what to give to the neural network. People were talking about, okay, I'll have the handcrafted features. I will take the data from the skin and I will tell, okay, this is the color histogram of the skin, this is mean value, this is standard deviation. But the problem is, are you sure? do we really need to have this kind of data? But we don't have deep learning at that time. And this whole idea of handcrafted features, so I'm merging computer vision a bit over here because they overlap. In 1959, Hubel and Wiesel did an experiment, and these two scientists got Nobel Prize in Physiology in 1980s for this study. They put electrodes in the brain of a cat and showed different stimuli, if you can see in the image. And they found that our brain has S cells and C cells. So they respond differently to different orientations of the edges. So they came with the idea that we need hierarchical learning. So this is some kind of hierarchy. And this idea was then captured by a scientist called Fukushima, and the invention was new cognitron. This is 1980. Does it look like convolutional neural network? Exactly same thing, same layers. Convolution pooling. But this was motivated by the study of Hubel and Wiesel, because they give this idea that we have convolution, our brain reacts to this different orientation, different way, and then on top of each other, they combine all of those stimuli. But 1980, convolutional neural network, no one knew before 2010, right? So again, one invention that was not used at that time. I have been told that I have only 2 minutes left, so I'll be quick. You can talk to me offline if you're interested in that. But impact of new cognitron, this picture on the left is AlexNet, beginning of deep learning. If you know what is ImageNet, this is the champion network, 2012. Exactly same as new cognitron. The only problem at new cognitron was there was no learning algorithm. They didn't know about backpropagation algorithm. But they had the idea in their mind, and that was captured later on. I'm skipping that. I have to, yes. This idea was captured by this guy, Jean LeCun, convolutional neural network. Everyone knows who is Jean LeCun? Chief scientist of Meta, a French guy. Okay, in 1989, he took the idea of new cognitron, combined it with error backpropagation, and voila, he has the network working for hand character recognition. It was a big hit at that time. At that time, SVM was also there. I'm not talking about SVM because I was just focusing on deep learning at the moment, but this is the same era when SVM was rediscovered. Have you heard of support vector machines before? Support vector machines were 1960s, rediscovered in 1990, till the guy moved from Russia to USA, to Bell Labs. When he published his article in Russian, no one gave importance. Same idea, 1990, everyone said, oh, wow, it's better than neural networks. Okay? This is how science progresses. Okay, okay, I'm just skipping that. This is something no one talks about much, but I guess without this restricted Boltzmann machine, we will not be able to train deep network. Because in 2006, Jeff Hinton showed that using, Jeff Hinton showed that we can use deep learning not only to classify, but to generate data. Beginning of generative AI, beginning of LLMs. Before that, no one knew, okay, can we learn probability distribution as a function now? Can we do that? No one has this idea. 2006, Jeff Hinton gave this idea, yes, you can do that, using restricted Boltzmann machine. Restricted Boltzmann machine is exactly like how our brain works. It's not feed-forward. We have a 3D structure. We don't know where is an input, where is an output. We have multiple inputs, multiple outputs. How to train that? No one knew. And this is the beginning of autoencoders as well. RBMs are predecessor of autoencoders, and then GAN or GANs. Okay, okay, I'm skipping autoencoder. AlexNet, that is the slide I showed you earlier. ImageNet is a challenge that has 1 million images around I think around 1,000 categories. Because of this one challenge, we have AlexNet, VGG, GoogleNet, ResNet, DenseNet. All of these, I think most of you has used or have studied. Maybe some has published something using those networks. These are all because ImageNet challenge. They were all proposed for ImageNet challenge. Beginning of generative adversarial networks. Ian Goodfellow. He wrote this book of deep learning. If you are a student of deep learning, probably this is the first book we recommend to have. Okay, I'm just skipping that, I think. Okay, can you recognize these faces are real or fake? These are all fake faces, by the way. These are all fake faces generated using generative adversarial network. And predecessor was autoencoder. Before that, there was restricted Boltzmann machine. Before that, there was backpropagation. These are all pieces of jigsaw puzzle. If you don't understand this puzzle, you will not understand where we are and how we have reached here. Okay, last but not the least, I have skipped LSTM, I have skipped RNN, because with transformers, with large language models, we are not talking about RNN anymore. But what transformers has done, that now we know how to encode long-term dependencies. If you have 10,000 pages digest or a novel, and in the last page it says, and then they found that Jim is the murderer. What is meant by they? Can you infer back? Because they was given their definition of they was like 10,000 pages before. How to encode that? Transformer has this ability because it overcomes decaying gradient or vanishing gradients. If you have vanishing gradient problem, only a couple of layers will be trained, and all the layers before that will not be trained. So transformer has this idea. Transformers are large-scale correlation matrices, value key, you know. So, if you talk to me in terms of mathematics, they are like gigantic matrices with lot of correlations going on. That's all transformers do, with lot of fancy words. Okay, vanishing gradient. Okay, I'm just skipping that because I have stepped the time. I think this is the most important slide. Where we are heading. So we started with Turing paper. We have I haven't talked about information theory, but without information theory, we'll not have entropy, we don't have information gain, we don't have KL divergence, which is the basis of GAN again. Then we have first AI winter, after perceptron, as I told, because perceptron cannot learn more than a linear surface. 80s was expert system, but later realized that probably they are not fulfilling the promise it has. Second AI winter came. And then revival was restricted Boltzmann machine or deep belief network. Without that, we will not reach the point where we are. 2012, beginning of convolution neural network, big revolution. But this is based on new cognitron, 2012. 2017, transformers. I'm not sure where we are heading, but the problem I see is AI community is promising a lot without considering the ethical implications, the impact it will have. I'm not sure we are heading towards third AI winter, because we will not have winters like we have before, because AI is part of our life. But where we are heading is a question mark, because we could have a lot of implications if we are not mitigating all of those concerns and the problems of AI. So this is where research lies, where we need to put efforts on, and probably this is the area open for research. Okay, thank you very much. Thank you. Do we have time for a question?
Thank you so much, Dr. Khan, for that illuminating perspective on where artificial intelligence has come from and where it's headed. So our next keynote is by Professor Dr. Hussein Arsalan, Dean of Engineering, Istanbul Medipol University, a leader in physical Mac research, and IEEE fellow. Professor Arsalan is internationally recognized for pioneering cognitive radio technologies and charting the path from 5G to 6G, highlighting new advances in IoT and smart connected systems. His talk is titled, "Are we ready for 6G vision? What's next? Flexible and cognitive radio access technologies for 5G and beyond." So let's warmly welcome Professor Dr. Hussain Arsalan.
Okay, Bismillahirrahmanirrahim. First of all, I'd like to thank the organizers and the leaders of the Bahria University for the invitation. It's an honor to be here. This is my second time in the Bahria University, and I'm hoping that I will come over and over again in the near future, and hopefully we'll be collaborating with some of the faculty members here in the Bahria University. So, also, I would like to thank Dr. Rizwan for the great presentation. And I don't know whether, a presentation after his presentation is going to be interesting to listen, but I'll try my best. So my talk is going to be on communications, wireless communications. As you all know, over the last 30 years, 40 years, wireless communication has grown a lot. And it has grown so fast and integrated to our lives in different levels, starting with the voice communication and later with data communication. And nowadays, we are in the era of communication of everything, Internet of Things. Yesterday, we had some presentations, keynote presentations on IoTs and sensing. And with 5G, we had a very great vision of moving this communication, voice and data communication into a new era where we would like to develop a standard that can do everything, that can be used for every verticals, not just by human beings, but also for various industries, including agriculture, health, and electricity, water pipelines. So basically, we envisioned that all kind of devices, all kind of things can communicate with each other and can integrate with the human beings. So that was the vision. Of course, this communication could be in different terms, with different rates, with different sizes, with different costs, with different energy consumptions. And we never had such a technology, such a demand before, having one standard that can do everything, that can satisfy all the requirements, that can meet all the expectations. It's a life-changing vision. So that's what 5G actually is. I mean, every once in a while asks me, what is 5G? I think this is one of the best definition of 5G. And of course, some countries are deploying it, and I think Pakistan is also about to deploy it. In my country, Turkey is also going to deploy it in this year or next year in 2026. So what I'm going to talk about today is another vision, which is a 6G vision. How is it different than the 5G vision? And what are the things that's going to be added? And what we are working on as my group and the international community. And one thing that I also want to mention, yesterday and today, we heard about a lot on AI. AI is the biggest thing today in the world, and has been applied to many domains, very successfully to image and text. And as a wireless community, we also started considering about integrating AI to our communication networks. And I'll also talk about that. Actually, it wasn't really my intention, but
knowing that this conference has a lot of emphasis on AI and we have a lot of students working on AI. So I will also talk about what is the role of AI in our community. So let's get started. So this is the outline of my presentation. So I'll talk about the projections and industry view and my view of 6G. By the way, 6G is not there yet. Just started the 6G standards last month, and for the next 3 years, maybe 4 years, we're going to be developing 6G standards. Our wireless communication is all based on standards. So standards are very important. So what happens, in the communication, we first build the technology, future technologies. So I have been working on 6G over the last 4 or 5 years, actually. So even everybody was talking about 5G. When there was nothing about 5G, we always think about the future, what will be 6G, and then generating all these technologies of the 6G, potential 6G. And then once we have our pockets full, okay, with the new ideas, innovations, patents, and then we go to the standard and then push our ideas. Not just me, all the companies, okay, are going to the standards, and then they define the 6G, the requirements of 6G. What the 6G is going to be. Why do we need to have a 6G? And what are the applications? What are the use cases? What is the vision? And then after that, we discuss about integrating our technologies to make that 6G happen. And then, of course, some of those are going to be winners, some of course are going to be losers. Eventually, we built standard. And then all those patents, that is part of the standard, it's called standard essential patent. So if you develop standard essential patent, you're going to be rich, okay? You're going to be shaping the future. So in the past, actually, many companies like Huawei, like Ericsson, like Nokia, and many universities have developed patents, hoping that these ideas, patents are ideas, innovations, will shape the 6G. And that's basically where we are, actually. We already have some ideas on 6G. We already have our visions on 6G. Everybody has their vision. Huawei has their vision. Ericsson has their vision. In my group, we have our own vision. And then also, we develop our own technologies for this vision. So that's what I'm going to talk about first. What is the vision of 6G from industry perspective and from our perspective as well. And also, I will tie that AI. Why do we need AI? I mean, so far we never used AI in communications. All of a sudden, AI is becoming an integral part of communication as well. Is this a hype or is this real? And if it is real, how are we going to use it? There are different thoughts about this. I'll talk about that a little bit and the role of AI. And one of the important things in 6G, yesterday also there was a keynote talk, which is sensing. Up until now, including 5G, we always talked about communication, wireless communication. Communication is transferring information from one point to another point, either in the form of voice, data, whatnot. Sensing is different. I mean, sensing is known by the military, by the radar community. Rather than transferring data, we are transmitting a signal, unmodulated signal, non-data carrying signal. It's not carrying data. And we are receiving the signal. Either we receive or somebody else receive. It could be monostatic, I transmit, receive, or I transmit, somebody else receive. It could be either active, I transmit, and somebody else receives, or it could be passive. Somebody transmits a signal. It could be, again, data carrying signal or non-data carrying signal, but that signal interacts with the environment, and then somebody else extract information from that signal. This is what we call sensing. Sensing is becoming a very critical topic on these days. We are trying to sense everything, our environment. I mean, like sensing, like GPS is a sensing mechanism, sensing your location. Police radar is a sensing mechanism, sensing your speed, sensing your range, how far you are. But nowadays, these are macro sensing, sensing rough informations. We're talking about sensing micro level sensing, sensing your heart rate, sensing your blood pressure, sensing your sugar level in your blood, and sensing your agricultural information, sensing your electricity information, sensing the elderly people, whether they are lying, standing still, whether they are in a specific position inside the house, or they are going outside. So, like, think of everything that you can sense. It's going to be very important. So with the 6G, we are trying to integrate sensing with communication. So this is really integrating two different goals. So this is really a new game-changing, vision for 6G. And radio environment mapping as well, we call it RAM. Not only that, I mean, in the case of, for example, police radar, we have one device trying to extract information about speed or location or distance. We have a network to communicate. I mean, like two people communicating with walkie-talkie is something. Developing a network where, people can communicate with each other is something else. So cellular network, for example, is designed for communication of everybody. So there is a network behind all these phones that's working, and that network is extremely complicated. There are, roaming, handoff, moving, when you are moving, when you are, flying, you can always communicate. So that's possible because of this huge network, this complicated network. And there are networks, Wi-Fi networks, and different types of networks. So far sensing, except GPS is a network of satellites, but again, not really advanced network. It's a very primitive. So what we are trying to develop with 6G is a network for sensing, a very complicated, very advanced network for sensing everything. Okay? So imagine that what you can do with such a complicated, such a huge network. So that's the vision of 6G. Of course, all these things are great, beautiful. 6G is going to provide a lot of things for the humanity, and it's going to help our life. It's going to create, a digital environment for every sector. Every sector will be digitalized, will go through a digital transformation, but it will come with a lot of concerns. And one of the biggest concern is security, cyber security. So our lives, will be in danger. And then the wars of the future is not going to be with the weapons, with the tanks, with the rockets. So cyber security is the future world, and how the wars in the future is going to be. Therefore, security is extremely important. So while we are doing these networks through 6G, we are also trying to create a security mechanism, something that's ignored in the standards, something that's really not, emphasized in the commercial world. I mean, in the military, this has always been an important problem. The first problem, actually, the most important problem, signal intelligence, so that people cannot listen our signals. Mechanisms against jammers so that signals cannot interfere. Low probability of intercept, low probability of detection. People cannot, destroy our networks. Physical protection of the network, communication networks, communication devices. So all these things were important. But today, with the 6G, the number of threats is not limited anymore. So there are so many different ways that people can hurt us. Big companies, big countries can hurt us. So this is really one of the biggest concerns as a wireless engineer, as a academician, and also industrial person who has been working in this area. I'm worried about this severely, okay? And I need you to know that the future, as much as it is coming with a lot of, technologies, great technologies that can help the society, but it also comes with a lot of dangers, okay, with a lot of threats, okay? So saying that, our communities should work in these areas very carefully. We shouldn't let other countries, big companies, dominate these technologies, and then I don't want us to be the users of these technologies, okay? This is very important, maybe the biggest message of today. Yes, I'll tell you about all the details, but, I want you to listen all those things that I'm going to talk about with this mindset in your mind. So let's continue. Dr. Ridwan talked about the evolution of AI. Let me just briefly talk about the evolution of wireless from the first generation all the way to sixth generation. One of the main things that we have evolved is the bandwidth. Bandwidth is related to the data rate. The more band that you have, the more data that you can transfer, okay? So from the first generation wireless, the bandwidth was in the range of 30 kilohertz, 10 kilohertz, which is good enough for speech communication. But as the demand increased, the rate increased, we increased also the data rates. Today, with 5G, we are talking about 100 megahertz of bandwidth. With 6G, it's going to be 400 megahertz of bandwidth. So with 6G, definitely we are going to have faster and higher data rates. So it will come. It's in the packet, okay? But not only that, these kind of bandwidths are not available in the spectrums that we are using today. We have been using spectrum in the range of 800, 900 megahertz, 1.8 gigahertz, 3.5 gigahertz, 5 gigahertz, 6 gigahertz on these days. All this spectrum with the advancement of wireless technologies in radar, in communication, we used up all this spectrum. So there is no more room for us to go beyond, what we are, what we expect to provide, okay, what we are envisioning. So we have, demand, but we don't have the resources. One of the biggest resources for us is the spectrum. Power, of course, is an important resource, power, energy, but spectrum is the number one resource. So we don't have that availability in the lower frequencies where we are used to transmit, receive, and then develop devices, antennas, mixers, filters, all these RF devices. So what happened, okay, lately, we started exploring the higher frequencies, millimeter wave, terahertz, visible light. So spectrum is also being, okay, explored and available eventually for higher and higher frequencies. And also efficiency, spectrum efficiency. Rather than transmitting 1 bit per hertz, we learn how to transmit many bits per hertz, okay, like 20 bits. But this is basically with the advancements of the technologies that we developed over the past. And also some awareness capabilities, the adaptability and flexibility. So in terms of, the physical layer evolution, these are the things that we have developed from one standard to another standard. So we made our devices, our networks more intelligent, more capable, not only at the receiver, but also at the transmitter. The earlier standards were very dumb, and we used to call it, when I was working at Ericsson, standards are for dummies. All what they have to do, they have to connect the dots, as you see in this picture. There you go, you have a transmitter. But today, standards are for very intelligent people, like you see on the on your right-hand side. So it's so complicated, but it is so beautiful. You can create any picture. In the old days, you can create only one picture, one application, one vertical, but today you can create many, many slices. So not only again, the transmitter, receiver, but also we learn how to control the channel. Because in the past, the channel was the worst thing in wireless communication. It basically destroys your signal, and you have to do all kind of intelligence things at the receiver to compensate the effect of the channel. But today, we are also trying to control the channel by some mechanisms, by some network elements, so that we can not only, improve the channel or reduce the effect of the channel, but also we exploit how we can utilize these control mechanisms to improve the data rates, to reduce the energy consumption. So, long story short, we have developed so many intelligent mechanisms in the wireless networks, in the physical layer, MAC layer, network layer, at the transmitter, at the receiver, even at the channel, to make it so complicated, but so also efficient. Okay, so that's where we are today. Also, in terms of network, in the past we had one base station communicating with multiple users. We call it point to multi-point, point base station communicating with multiple points, or users are communicating with the base station. Base station was our anchor. We always connect to one base station. Wherever we go, okay, we find the closest, the best base station that we can connect. But only one base station. Today, we are now connecting to multiple base stations. In 6G, we are developing CRAN, centralized RAN, or cloud RAN, where multiple base stations can simultaneously serve multiple users. Okay, if one base station is down, due to earthquake or some disasters, you can always find another base station. It doesn't have to be the closest one to you. You can have ways to communicate with multiple of them. Okay, so that's something that we learned with 4G, enhanced in 5G, but it's going to be even better in 6G. And also we learn how to coordinate between multiple standards, multiple technologies. We have Wi-Fi technology, we have radar technologies, we have cellular technologies, so many technologies using electromagnetic spectrum. And those technologies are interfering with each other. But like I said, the spectrum is limited, so we need to learn how to coexist and how to use the same spectrum simultaneously in the same geographical area without interfering with each other. So this is a very difficult task, but we are learning and coming up with some mechanisms to handle that. Okay, and utilize different type of spectrum. Today, for example, all the operators are using licensed spectrum, but with 5G, we learn how to utilize licensed and unlicensed spectrum. In the future, we are going to also learn how to use different spectrum. If somebody owns a spectrum but not using it, we call it dynamic spectrum access. For example, radar technologies are actually, they are allocated a big chunk of spectrum, vehicle, weather radar, this radar, that radar, and they are occupying a large portion of spectrum, but sometimes they are not using. Also, terrestrial TV broadcasting stations, they are not using actually. If they are using, that's fine, but nowadays they are not using. We have satellites, we have fibers, we have cables, and the old days of broadcasting, terrestrial broadcasting, is not used in many developed countries. But those spectrum is allocated already, and that's a golden spectrum. So we are going to learn how to utilize that. So these are the things that we are working. Okay, I'm going to skip this, but just currently, we are in 5G advanced. The next version is going to be 6G, release 19. We call it release 19 because, even though we have 5Gs, 6Gs, but there are some intermediate standards that we always develop. Every 18 months, there is a new release. We advanced. So in the current release, release 19, we call it 5G advanced. We are working on these areas. One of the areas that I want to highlight is wireless AI and ML. So actually, for the first time, we are trying to utilize AI and ML tools to improve our communication standards. And also, for the first time, we are using our 5G standard and enhancing it to add some sensing capabilities. So this is where we are. But security is still missing in our standard, 5G advanced standard. And these are the things, technical things that we are working on 6G. As I mentioned, sensing is a big deal. Unified sensing and communication. How can we develop a standard? How can we develop a network, a technology that can sense and communicate simultaneously? And better integration of AI. In release 19, we made an attempt, but in 6G, we are trying to utilize AI in a better way. If needed, we call it native AI. We would like to design a standard with the intention of integrating AI into our network, into our radios. Okay, so the AI actually in the day one will be integrated into our standards. And in 5G, we wanted to serve IoTs, but we failed. Okay, in 6G, we want to do a better job. So better IoT services, unified RAN. Energy is #1 cost for, I was on the board of the biggest operator in Turkey, Turkcell. For the first time actually, the operation cost is less than the energy cost. So most of our cost, operating cost, is on the energy. So network is consuming so much energy. Your devices are also consuming energy. So for 6G, we are trying to find mechanisms to reduce energy consumption. And energy is related to the number of bits that you transmit as well. Because we are going to have more bits to transmit. Compared to today, we are going to consume, if we don't do anything, we are going to consume 100 times more energy. And eventually, the energy consumption of our networks is going to dominate everything else. So unless we come up with some techniques, or you can just drop your phones and then give up on using this technology. But nobody is going to give up. Today, actually, you can give up on everything. Okay? Even your keys, your wallet, the only thing that you don't give up is your phone, okay? Your wireless devices. I mean, in the past, you could have lived without water for 1 day, maybe 2 days for some of you, without food for a week, maybe a month without food, but without a cell phone, without connection, you cannot even last half a day. I mean, I can't, I don't know about you, but so we are so addicted to this technology. So unless you are going to drop it, okay, there is no other way of solving this problem, energy consumption, unless we come up with some techniques. And that's what we are going to be working on for 6G. And there are some other things. Another thing which is very important is NTN. So far we have been using terrestrial networks for communication. Terrestrial networks, all these base stations, Wi-Fi access points on the ground. As you all know, non-terrestrial communication is becoming a big deal. I mean, Elon Musk's Starlink and many other examples. Amazon is developing another technology. UK is developing another technology. All the big companies are adding, not moving, but adding another layer of network, which is terrestrial network. Mostly today is LEO, low orbit satellites. But in the future, it's going to be in the form of balloons, drones, LEOs, GEOs. GEOs are available everywhere. Almost all countries are deploying GEOs for mostly broadcasting. But LEOs are mainly for communication, broadband communication. Not only broadband communication, for sensing. Not only for sensing communication, but also for controlling the world, okay? I mean, Iridium, Starlink, has the aim of providing wireless service to the rural areas. But the major thing, I think, again, this is my opinion, it's not written, but the way it's written, it is just rural area communication. But I think the most critical thing here is to compete with China, because China is #1 in terms of wireless technology today. Huawei is the best company in terms of wireless, and they can't even compete with Huawei. Nobody can compete with Huawei. So the only way to compete with China is to have a network, and that network should be global, because those satellites are moving around the world and covering the whole world. And then today, the #1 thing in our technologies, again, look, The way that I describe 6G, all the technical things is, okay, like better communication, better sensing, better this, better that, high data rate, low power, low energy. But at the end of the day, the competition is reaching to the data. Who can have better access to the data, information? In the future, everything is going to generate data. That's why we have IoTs, networks, sensors. Your soil is going to generate data. Your refrigerator is going to generate data. Your heart is going to generate data. Your car is going to generate data. All the Teslas are generating data. You can control Tesla with your cell phone. You can get a lot of information from Tesla within your cell phone. But Elon can also get the same amount of information. You can control, and Elon can control also your Tesla. Not only Tesla, your agriculture, your soil, your electricity infrastructure, your water infrastructure, everything with 6G can be controlled. And everything can generate data. That's what IoT, that's what 6G. So the race of today is who can have access to the data. The more data that you can have access, the more control that you are going to have, the more superpower that you are going to be, the best brain that you are going to have. Our professor already discussed about how important the data. Yesterday we had a lot of things about data. AI is all about data. AI is, you can have super AI, super brain if you have data about everything. Health data, for example, is very important. Today, if you have all the data about health, you can have better medicine, you can have better diagnosis, you can have better treatment. Okay, the data is very important. A doctor, a single doctor, an experienced doctor doesn't have that much data. So the future of medicine is going to be, I believe, is about data. So the race is reaching to the data. Whoever can get access to the global data, all the data in the world, will be the superpower, and then we'll create super brain. Doctor also said that how many synapses that we have in our brain? How many synapses that we have in AI today? Our brain still has more synapses than the AI. So how do we get a better brain if we have more synapses? How do we get these more synapses if we have more IoT devices? If all of them are connected with each other, if all of them are gathered, okay, if we can combine all these things, then you get the super brain. Then you get the super AI. So that's the race. That's why we need NTN as well, integration of NTN and TN all together. So my vision of 6G is these four things: intelligence, communication, sensing, and communication. Integration of all these things. Communication we already had up until now. Sensing we didn't have. I already talked about sensing, how important it is. And intelligence, if we can integrate intelligence, intelligence means making our networks more intelligent, but also creating intelligence from our network. So far, we always talk about using intelligence to make more efficient networks, but the future is using networks to create intelligence. Like I said, if you have more devices collecting data, transferring data, if you have a huge network, then you get that intelligence, better intelligence. So if we can integrate intelligence, communication, sensing, and security, that's going to be the 6G, my vision of 6G. And I'm going to relate that actually with what I have done 25 years ago. If you look at this slide, this describes the 6G of my vision. Basically, having a very flexible radio access technology platform with better modulation, better coding, better waveform, better control of the channel, better interference management, all the things that I mentioned. This is the red thing. The red one is more related to radio access technology. We need to have very flexible, very powerful radio access technologies, which we didn't have in 5G. That's what we are working on 6G. But that's not enough. If we have that flexibility, the question that we need to ask, how can I utilize? I mean, like, remember those dots, so many dots that we have. How can I connect all these dots to create a useful vertical, useful picture? That's basic adaptation. Utilizing these flexible, very powerful radio access technologies to create a beautiful vertical slice. We call it network slicing or RAN slicing. Every slice is an application for a sector. Whether it's an agriculture, whether it's automotive sector, whether it is a health sector, we need to create this red square, beautiful radio access technologies, which we are working, which my students and also the community is working, but at the same time, learning how to utilize these beautiful radio access technology platform and enabling some adaptive techniques, optimization techniques. But again, sensing is also important because adaptation requires knowing, understanding the user's requirement, understanding the channel. If we can sense, if we can learn about the user, about the application, about the environment, then you can go and adapt properly. So that's basically part of it. And then reasoning, learning. So if you can connect all these things, then there you go. You have the cognitive radio and cognitive networks. That was my vision 25 years ago, which I couldn't realize because we didn't have those red square at that time. And we didn't have that AI and ML at that time. We had some primitive version of it, but we didn't have the supercomputers, super machines at that time as well. So now we have. So now it's time to realize this cognitive radio and cognitive networks and then, close this loop. But AI and ML plays an important role in this, to realize this. Where do we use AI and ML? You can use AI and ML to create that flexible platform. There is an arrow from here to that red one. You can use AI and ML for sensing. You can use AI and ML for adaptation. You can use AI and ML for reasoning. You can also use AI and ML for creating security in our networks. So AI and ML is going to play an important role for our future communication systems. What kind of a role it's going to have and where do we integrate, how do we integrate is a question today. In the standards, 6G standards, there are some applications the companies are envisioning and then utilizing, and then results are good. So far, we always use models, we always use math, we always use physics, we always wanted to understand what's going on. Today, there is always, like wireless community is split at 50-50. 50% hates AI, the other 50% loves AI. And me, 2 years ago, I hate it, okay? Because I think that I don't like black box. I don't like black box solving all my problems, not knowing how it's solved, okay? I always wanted to know and get the intuition and understand. How many minutes I have? 5 more minutes? Okay, I'll wrap it up. So that was my thinking, okay? Because I also have background on how to make things happen, how to design a transmitter, how to design a receiver. I have models, and it works so far. Why would I risk with a black box doing some of the things for me, not knowing how it did it, okay? So I was resisting. Today I changed my mind, okay? Maybe Yusuf Hocam is gonna say different things. He's an expert in AI, ML. He may have suspicions or he may be the biggest lover of AI. So I am kind of mixed. I have mixed feelings, okay? And doctor also said that there are winters after summers. We have seen 2 winters already, but we are in the summer, like a big summer, like long-lasting summer, as if like there is no winter is going to happen. But every summer comes with a winter after that. So I think that, this hype is going to slow down at some point, okay? But no matter what, that's a philosophical thing. But what I'm thinking is, for example, Nokia has a vision of AI ML. So their vision is, I don't agree with it at all. Eventually, they think that they can replace the whole transmitter with AI ML, and then they can replace the whole receiver with AI ML. So we don't have to know any domain knowledge. We don't have to, so that's a very dangerous thing, okay? So I don't have to teach my students information theory anymore, communication theory anymore. I don't have to teach them the random process, probability. I don't have to teach them waveforms or modulation. So why? Because AI can do everything, okay? You don't have to know anything. This is very dangerous, okay? And they won't have any intuition about, how things are working. It works, don't worry about it. This is very dangerous. So I don't think this is the right path to go. But at the same time, just ignoring it completely is a dangerous thing as well. So what I recommend my students, I have a lot of Pakistani students, by the way, 15 in my research group, PhD students, and also from some other countries, but I love Pakistani students. If you are interested in working in these areas, by the way, this is an advertisement, sorry, I have to inject it. So looking forward to working with you. What I tell to my students, okay, you are not allowed to work AI ML until you know all the theories, all the domain knowledge, okay? The only guys who can work on AI-based solutions who knows the domain very well, who can relate the output of AI ML with their theories, who can have two results, one with AI ML, one without AI ML, and then relate them. Eventually, what I want my students to do, if they can just learn from AI ML, learn from it. Even if it is black box, you can learn from it. That's what Hatta did. That's what Okumara did. Okumara and Hatta collected a lot of data and then used their domain knowledge about free space path laws and then tried to explain how this data is related to physics. Eventually, they didn't match. Physics and the real data is not working together. So physics is telling me one thing, data is telling me something different. But what he did, he used his intuition about the relationship of antenna, height, environment factor, this and that. He added all these correction factors without using AI. Of course, he used his intuition. But we can do even better than that. So AI here is a very good tool, but it's a tool. For me, it's a tool. For somebody else, it may be a science. For me, it's a tool. It's an excellent tool to help me generate knowledge. If you can use AI to generate knowledge, to generate science, to enhance your domain further, then we are going to use AI. But the first thing that we are going to do, understand the domain. The second thing, and use AI, and then how to improve your domain. With that, I'm going to conclude my presentation. Thank you. Questions? Do we allow questions? No? Okay. So I asked whether I can have a few questions, but they say that time is limited, so maybe like during the breaks. Okay? Thank you.
Thank you, Professor Arslan, for a visionary look at the wireless networks of tomorrow. We are delighted and honored to have Rear Admiral Ahmed Fozan, Hilal-e-Imtiaz Military, Pro-Rector Research, Innovation and Commercialization, Bahria University. Sir, your presence enriches this session with dignity and inspiration, and we sincerely value your being here. To conclude this morning's session, we will now present mementos to our keynote speakers. I kindly invite Rear Admiral Retired Ahmed Fozan, Hilal-e-Imtiaz Military, Bahria University, to please come on stage to present the shields. First, may I invite Professor Dr. Rizwan Ahmed Khan to the stage to receive his memento. And now may I invite Professor Dr. Hussain Arslan to the stage for his memento. Thank you, sir. I now warmly invite all our guests and delegates to join us for tea break at the Faculty Cafe. Thank you.